Before we look at the specifics of the sine curve or sine wave, let's take a look at periodic functions in general. A curve that repeats its shape over and over again is called a periodic curve or periodic waveform. And periodic waveforms have certain characteristics. For instance, if we start here at point 0 and follow this waveform, we can see that it is going to repeat at this point and continue on over and over again. So from here to here is called the period of this waveform, or one cycle of the waveform. Now in terms of waveforms, we're going to find that there's an amplitude, and the amplitude is the distance from this point up here, but the distance from here to here is called the peak-to-peak value. And the peak-to-peak value is really this amplitude plus this amplitude added together. The x-axis represents either an angle, as we can see here in degrees, or it can represent radians, or it can represent a time scale here, say in milliseconds, microseconds. The period is the x distance taken for one cycle between here and here. Say this is 1,000 milliseconds. This would be 2 pi radians for one cycle, or this could be 360 degrees for one cycle. So that is the period here, and the frequency is 1 over the period. Units of frequency are cycles per degree, cycles per radian, or most commonly cycles per second, called hertz, depending on the units of the period. The amplitude is half the distance between the greatest and the least value here. So this here is the amplitude, which is 1, and the peak-to-peak value is going to be this amplitude plus this. This would be a unit of 2. The instantaneous value is its y value at any point x. So if we click here, that's 90 and 1. And if we go down here, we can take a look at various angles, such as 45 degrees, which is 0.707. We can look at 30 degrees. The sine of 30 degrees is 0.5. Let's take a look at this diagram of a voltage curve. This is the voltage along the y-axis and the time in milliseconds across the x-axis. And as we see here, this pattern goes to here and then repeats. So the period here goes from here to here, which is 20 milliseconds per one complete cycle. And the frequency is 1 over that, which works out to be 5 hertz. The amplitude here, it goes from here to here, so that's 50 volts. And the peak-to-peak is double that, which is 100 volts. The instantaneous voltage at 50 milliseconds, which is here, works out to be 12 volts, as you can see here. In order to graph a sine function such as y equals sine x, you can use a table where you have the degrees in 30-degree increments, such as 0, 30, 60, and so on, and figure out what the sine of these are and plot them on a piece of paper in pairs. A better way is to actually use some software online that will do this for us and give us a better representation of our sine curve. Let's take a look at that. Now there are a number of places online that allow you to graph various functions. One is called desmos.com, which allows you to use a graphing calculator. And it comes up with a grid here and allows you to create things such as a sine wave here that's in degrees. It allows you to create a sine wave that's using Radian Measure. And it can also allow you to create one that's using a time base, say in milliseconds versus amplitude here. So there are various ways to do this without having to use your own graphing and sketching. Let's take a look at this one here. And again, if we go to 90 degrees, we click on this, 90 and 1, 90 degrees and 1. And if we go along the curve here, we can get down to 45, which is 0.707. If we go down here, we can get to 30 degrees, which is 0.5. We can get down to 0, which is 0. And we get down to minus 90 here, which is minus 1. We can also use a calculator to figure these out. For instance, 90 degrees, so we put in 90 degrees. We hit sine, we get 1 here. If we put in 90 and change sign and do a sine of that, we can see that this is indeed minus 1. So there's a number of ways to generate this, but this is a very useful way here, just by clicking on various parts of the curve and finding out what the actual sine value is as we go from minus 360 to 360, or if we go minus pi to 2 pi, or in the case here where we're going from minus 1000 milliseconds up to positive 1000 milliseconds here. Now if we want to graph, instead of y equals sine x, y equals a sine x, where a is the absolute value of the amplitude of the sine wave. And when we do that, we can change the amplitude from just being 1 here with a given period and frequency to any value that we want. In this case, it's saying y equals 3 sine x from x equals 0 to 2 pi. Let's see how we would set that up using Desmos. When you're in this utility, you can click on the little wrench here and be able to set up things whichever way you'd like. Right now the default is radians, but we can switch to degrees or radians, but nothing's going to change here until we start setting up our x-axis. So for instance, let's set up our x-axis to be minus pi divided by 2 to give us minus 90 for that side. And let's set this up to be 2 pi plus 1, just a little bit past pi. But the thing that's going to change this here is changing our step size here to be pi divided by 2. And now we can see that our units here have changed to be minus pi by 2, pi, and so on. So that's first thing we want to do. Now the y-axis, if it says 3, let's change this from minus 4 just to give us a little headroom here. Let's change this to plus 4 here, and that gives us what we need here. And so we've got our grid pretty much set up. But what we want to do is now say y equals a sine x. Now notice it's got a slider here, so we can click on that and then we can see what's going to happen as we move our slider. So if we go all the way up to 3, this is exactly what we've got now for the function that was given previously. Y equals 3 sine x, and it's going to go over our 2 pi here, and we can see that changing the amplitude changes the value from here to here. Again, the peak value is double that. Now notice our slider goes from plus 10 to minus 10. We can click here and change this to be, say, minus 4 to plus 4. And when we do that, let's try changing this now so we can see that it's going to go all the way up to 4, which is our maximum that we set on our screen here, and all the way down to minus 4. Now watch what happens when we hit 0. When we hit 1, it's our regular sine wave. But if we hit 0, then there is no amplitude. It's just going to be flat line. But look what happens when we come back up the other way. Our sine changes phase. It goes in an opposite direction, doesn't it? So let's compare this to our original one. Let's go back here with a equals minus 1, for instance. And let's add another wave here. Let's just add y equals sine x. So if we take a look here, this is our y equals sine x is the green. This is the one that we saw originally. And if our amplitude is -1, it actually changes it to the complete opposite of that wave. And if we switch it back here to 1, notice that they line up again. So changing the amplitude will actually change the phase of the wave to be completely 180 at -1. And as we continue, it's going to then just make the amplitude bigger in the opposite sense. So as we change our amplitude from positive to negative, you can see what it's doing here. What we can do is get rid of any of these at any time just by clicking here, clicking here, clicking here, and getting back to our default grid that we've set up here using our little wrench. Now if we want to go from Radian Measure, and we can actually put in here a label here of radian, and you can see that it does tell us that it's radian, which is what we've got set up here. But we can change this to degrees. Let's switch over to degrees, and let's change the title here to be degrees, and let's change the title here to be amplitude. Now to make this show in degrees instead of pi, radians, and so forth, what we have to do is go back to here and set our defaults here. So let's go here and change this to minus 362. Let's change this to be positive 362 just to give us a little headroom, and let's have our step size here of 45 degrees. And what we've done is we've changed everything back to degrees from here, and let's plot again y equals sine x, and we can see that this is what we're getting here. We can also again plot here, so add another function, y equals a sine x. And again, let's put in our slider. Let's just shut this one off for now, and let's take a look at this one here. And again, we can change our slider, and you can see that it does change the phase, but we haven't again changed what our maximum is here. So let's change our maximum here to be -4 to a maximum of +4. So as we change our slider when it's at 1, that's exactly the same as this wave here, as we can see. If we change this to -1, and it goes back through 0 and then goes up the other way, let's go to 1, and again it's going to be the complete inverse of this wave here. So that's what the amplitude does, whether you're talking about degrees, an amplitude here, radians, whatever. And again, what we can do is if we click on here, we can see 90 and 1. We can see all these various things as we could on the other one as well when it was in radians. Now what I've done in this instance is I've taken out everything else and put in a new function, y equals a sine bx plus c. Right now I've basically disabled it just by clicking on it, but I can enable it just by clicking here. So let's go back over y equals sine x. Y equals sine x means that it's going to go from here to here in one complete cycle in 360 degrees. And the amplitude here, because there's nothing for amplitude, will always be 1. So the sine of 90 is 1, the sine of minus 90 is minus 1, and the sine of 0 is 0, and so forth. So this is our basic sine. Let's take a look at this one. Now I've made some changes here, so please be aware. So what I've done is I've gone here and I've made a minus 4 to positive 4 to fit within here for our amplitude. So make sure you make that adjustment for a when you set up this equation. Also for b, let's take a look. B just goes minus 10 to plus 10, which is fine. Just leave those defaults. But for this one, what I want you to do is go minus 365 to positive 365 for c. Make sure this is originally 1, 1, and 0. So if we do have all that set up, then if we look at this, these are exactly the same waves. There's no difference between them with these defaults. Now what we've seen before is if we change our amplitude and increase our amplitude, that's all it does. And it's going to go up to our maximum of 4 here. All it's doing is the A in front changes the amplitude of this wave. And the amplitude in this case goes from here to here. So our amplitude is 4. Our peak to peak here is 8. So as we reduce this and back to 1, it ends up being exactly the same waveform as before. But if we start going in this direction, we're decreasing our amplitude right down to 0, where it is flatlined. And then if we continue on, we're going to see that our amplitude is increased 180 degrees out of phase. And you can see that again it goes minus 4 to plus 4. And again, when we go back here, the amplitude is going to be for the wave as given here. So let's take a look back and put this back to 1 and see what the other sliders are going to do. Now b equals 1, everything lines up again. But let's take a look at changing b here. Let's make b 2. Okay? So let's take a look at original wave. And our original wave here goes from here to 360. So the period of this wave is 0 to 360. That's the period between here and here. But if we flip this one in and decrease this, we can see now that the period of our wave is half of that, which means our frequency is double that. So whatever frequency we had before with this wave, the frequency is, say if this is frequency of 1 unit and a period of 1 unit here, what we've done here is we've increased the frequency by double by making the period half. So this is really changing the frequency. The B part here is changing the frequency of our wave. So let's just see what that means. As we go higher and higher, we can see that as the B value increases, the frequency increases because the actual period of the wave, let's get up to 8 here. So if we take a look at this one, we can see that our period is now 45 instead of being 360. So our period is a lot shorter, but our frequency is 8 times higher. So this changes the frequency of our wave. Let's go back again to where it's 1 and it's equal. And again, if we go in the opposite direction, we're going to find that our frequency, let's go to minus 1 here and compare that to original 1. Again, it's completely out of phase. And as we keep going in this direction here, we're going to increase our frequency and decrease our period of our wave as we slide this to the left. So this B here adjusts the period and the frequency. Let's go back and put this back to 1, so it's the same as the other wave. And let's take a look and see what this C does here. Now we've got it minus 365 to 365 with C equal to 0. Let's take a look at sliding this, and look what happens as it gets higher and higher. We're changing the actual phase of the wave. It's changing its position here all the way up to being completely locked in again at positive 360. And if we move it in the other direction, the phase is changing again all the way down to minus 360. So it actually lines up again. So this is changing the phase of our wave on our degree line here. If this is at 0, then everything lines up as before. If we look at the sine wave y equals sine x, which we have here selected, we can see that this produces something called a fundamental. And the fundamental goes through one complete cycle within 360 degrees. Now if we look at the more generic equation, y equals a sine bx plus c, this means that a is 1, so the amplitude is 1 here. B is 1, because we have one complete cycle within 360 degrees, and c is 0. So we've changed this now here to be the same, with one difference, that instead of b equal 1, which we have in this case here for one complete cycle, b is now 2. So let's see how that looks different. So in this case with b equals 2, and we switch to this wave here with b equals 2, we find that this has two complete cycles within the 360 degrees. And the period, as it says, is 360 over b. So if b is 2, 360 over 2 gives us 180 for one complete cycle. So the period is going to change depending on b. If b doubles, the period is half, but the frequency, being 1 over the period, is going to be double. If we look at b equals 3 now, we have 1, 2, 3 complete cycles here. So the period is going to be 360 over 3, and that is going to give us 120 here. Now if we look at this fundamental waveform y equals sine x, we can see here that the period is given by 360 over our coefficient here, and our coefficient here happens to be 1, and c is 0. So in this case, this would be 360 over 1, which means that one complete cycle happens in 360 degrees. If we look at our frequency is 1 over that. So if we say 1 divided by 360, this is going to give us the number of cycles per degree. So when we look at 1 degree, it gives us this amount of a complete cycle here. If we were to multiply that by 360, then you can see that indeed that is going to give us the entire wave here when you multiply it by a complete waveform here. Let's take a look at this other example here where everything is the same except we've changed b to be 4, leaving everything else the same. So let's look at that other wave. So as you can see, our period is 360 over b. So if we put 360 divided by b, which is 4 in our case here, we're going to get that our period is 90 degrees. So if we go from here to one complete cycle, that is 90 degrees, because we have a total of 4 complete cycles for 360. Our frequency is now going to be 4 divided by 360, which is this value here. Now if we take that and divide it by our other frequency that we had here, we can see that it's 4 times the frequency. So increasing this to 4 has increased our frequency by a factor of 4, but it's changed our period by a factor of 1/4 of the entire wave here. Let's take a look at example 6 here. It says find the period of the sine wave y equals sine 4x. Now if we have a is 1 here, and b is 4, and c is 0, this is exactly what we have here, y equals sine 4x. And this is the wave that we've seen before. Now it says the period is 360 divided by 4, which is equal to, again, our 90 degrees. Now if we want to express this in radians, if you remember, 2 pi radians is 360. We divide that before, we get pi by 2. And if you remember, pi by 2 is 90, pi is 180, 2 pi is 360. Let's now look at example 7. It says determine the amplitude, period, and frequency of the sine curve y equals 2 sine pi by 2x, where x is in radians. And it says graph one cycle of the curve. We have y equals 2 sine pi by 2x. So if we take a look, a is definitely 2. As we can see here, we've got an amplitude of 2. And b is equal to pi by 2. This was what we can see here. So the amplitude is 2 and the period is given by 2 pi radians over pi by 2, which works out to 4 radians per cycle. So every cycle will have 4 radians, as we can see here. Let's take a look at this equation here. Y equals 2 times sine of 2x. Now if we compare that to the generic equation here, the 2 here is our amplitude, and our amplitude here is 2 units. Our peak to peak is double that, which is 4 units. The b here is the number 2, which means it's going to take 2 complete waves to get to 360, which affects both our period and our frequency. And then we've got c, which is a number down here. Now right now this is this wave here, and if we switch to this wave, we can see that these two waves are identical. Why are they identical? Because the A is 2 for both of these, the B is 2 for both, and right now the C is 0. Let's see the effect of changing the C. So we're going to move it in this direction, and you'll notice that the wave here, this wave here in blue, is actually moving in the opposite direction. As we make this negative, it moves the blue wave in this direction here. Now this is called phase shift, and phase shift is given by minus C, which is this number here, over B, which is the number of waves to get 360 degrees here. Let's do the calculation here to see how much that wave, the blue wave that was in sync with this, is actually shifted. So this is minus 180, so it's minus C, so that'll be positive 180 divided by B, which is 2, and that gives us a 90 degrees phase shift. Well, let's see if that's true, because this wave here, the peak of it is at 135, so let's put in 135. And let's subtract where the other wave is at 45. And yes, indeed, we can see that there was a 90-degree phase shift. So as we move this more negative, that makes this wave move more and more to the right. Let's see what happens when we move the wave past 0 again to a different number. Let's try this number here, 180. And here's our original wave again. And let's just see what that does. So if we look at the calculation here, this is 180. So that's 180, and it's negative of that, divided by B, which is in our case 2. And again we have a 90 degrees phase shift. But in this case the phase shift is going the other way. So from this peak to this peak, I think you'll see is a shift in 90 degrees because it's all moved in this direction here. So when this becomes positive, the wave shifts this way. When this becomes negative, the wave shifts in the opposite direction here. Now if we take a look at this wave, y equals sine x plus 45, where 45 is our phase shift. Remember, our phase shift is going to move to the left because this is a positive value, and it's minus c over b is our phase shift. Let's work out our phase shift here. It's minus c, which is 45, so that's 45 change sign, divided by, in this case, b is 1. So this means there's a 45 degree phase shift to the left. So if we look at a standard wave y equals sine x, which is this one, I think you can see that the peak here is 90 and has indeed shifted to 45, which is a 45 degree phase shift to the left. Let's take a look at our y equals sine x waveform here, where it takes one complete cycle to go to 360 degrees, and that we have an amplitude here of 1, and we have no offset. And then let's take a look and see how these various things such as amplitude and period and offset work here. So let's just compare by clicking on this and letting the amplitude change. So as we can see here, as the amplitude changes here, it's going to change this up and down to the minimum maximum of that value, which in this case is plus and minus 2. You'll notice also when it goes negative, it's going to change the actual way the waveform is. It's going to be inverted. Next, let's take a look at B, which is going to affect here the period and frequency. So as our value goes from minus 2 to positive 2, you can see that there's 2 waves instead of 1 wave, and again it inverts it going the other way. And finally, let's take a look at how changing C here changes our phase by a factor of minus C over B. So as it goes positive, the wave phase shifts to the left. As it goes negative, the phase shifts go to the right.